Hello, my name is Martin Dvořák. I come from Pardubice, the Czech Republic, and I am currently a student of Artificial Intelligence at the Faculty of Mathematics and Physics of Charles University in Prague. My interests are in the area of discrete mathematics, theoretical computer science, and also in design of intelligent agents for virtual environments. I view mathematics as a great adventure where you learn something new every day. It's a great adventure of increasing your levels of abstraction, a walk through wonderful land where you discover new connections between things all the time. I really enjoy solving puzzles and creating mathematical proofs. I don't view mathematics and computer science as two separate fields. Instead, I view them as one field because unlike physics and chemistry and biology, where you have to go to the real world and observe and measure and study whether your theory holds in the real world, mathematics and computer science have in common the fact that they are purely abstract. You define something and then you study the properties of the thing you defined. It's very abstract, but it doesn't mean it doesn't have practical applications. Both mathematics and computer science have great practical applications, but the way they are built is very abstract and you cannot draw a line between mathematics and computer science. Of course, there are some differences. Mathematics is more about existential properties, whereas computer science is more about computational properties, but you can't divide the two things completely. For example, a mathematician might ask whether every game of one kind, every game of some type, has Nash equilibrium, and computer scientists will ask how to compute the Nash equilibrium, but you see that you cannot divide these questions completely. Having an algorithm to compute something can be a proof that something exists, and many mathematical ideas are bases of ideas in computer science. Let's go back to my research interests. I would like to tell you about my bachelor thesis. My bachelor thesis dealt with symmetric cryptography. My goal was to implement data encryption algorithm based on cellular automata. I was inspired by Stephen Wolfram's book, A New Kind of Science, where he discovered that cellular automata, which are very simple systems with very simple rules which are applied repetitively, can exhibit very different behaviors. Some cellular automata quickly converge to something, or they have very repetitive behavior, but other cellular automata are Turing complete. And there are also cellular automata that exhibit great pseudorandom behavior. In fact, when you look on something they generate, you can test it using state-of-the-art pseudorandomness tests, and you will discover that they produced high-quality pseudorandom data. And that inspired me to develop cryptographic algorithms based on cellular automata. Not only that cellular automata are very simple, but they are also very local. Their rules don't look far away. So this means that such an algorithm can be very efficiently parallelized, and you can also create specialized hardware that computes cellular automata very fast. First of all, in my thesis, I needed to develop a library or framework to play with cellular automata. I was using C# for this task, and I developed a high-quality object-oriented approach how to play with the cellular automata and the algorithms, so that I was able to specify separately what kind of cellular automata I'm using, what parameters I'm giving to the cellular automaton, and what algorithm I use to perform encryption using the cellular automaton. So it was very modular, it was very flexible, and I was able to perform many experiments with many combinations of these things. The result of my bachelor thesis was, apart from a WinForms application that provides the encryption in user-friendly way, the main output was a thorough analysis of many cryptographic algorithms based on cellular automata. And even though neither of the algorithms proved to be practically useful, I think it was very interesting. At least it was very interesting to me. Now, in my diploma thesis, I worked with artificial intelligence for games. I tried to develop artificial intelligence for Bridge, which is a very old, very famous card game. More specifically, I tried to develop bidding system using evolutionary algorithms. The Bridge consists of two parts. There is bidding part and there is card play part. The second part, the card play, has been already solved by artificial intelligence very well. There are effective algorithms that can beat even the best professional players. However, the field of bidding is much more problematic. There isn't much of successful research done there, and all useful AI systems for Bridge use human design bidding rules. So it is based on something that people discovered by playing the game. But what I'm trying to do is to let the program design the bidding system on its own, and for this purpose I use things like genetic programming and learning classifier systems. And I am really interested in whether I can develop a bidding system that can beat good human players. In my future, I would like to do research in theoretical computer science, maybe some discrete optimization things, and maybe artificial intelligence for games. I don't have a very narrow focus, so I think that your system of rotations in several research groups would suit me very well, because now I don't know what exactly I want to study, but I think that if I go through several research groups from my interests, I might discover what is good for me and what I devote my life into. And because I heard from my friends that your professors are extremely intelligent, extremely skilled, and really good in supervising research projects, I think that a PhD study at IST Austria could be a great way how to start a potential scientific career. Therefore, I'm applying for my postgraduate study in your institute.